students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as interference of light. Now, let's see this. What do we understand by principle of superposition? Principle of superposition of waves. Now guys, we are still assuming that light travels in the form of waves, right? Let us assume I have a point A here. I have light coming from this source in the form of wave, and I have light coming from source C in the form of waves. Then what will be the net effect at point A? The net effect at point A will be the sum of the two waves, and that is called as principle of superposition of waves. The net effect, will point A be bright or dark, will depend upon the vector sum of the waves reaching point A from B and C. Fine, that is called as principle of superposition of waves. So what does principle of superposition of waves state? When two waves traveling through a medium traveling through a medium arrive at a point of the medium simultaneously, arrive at a point of the medium simultaneously, each wave produces its own displacement. Each wave produces its own displacement at that point, independently of the other, and the resultant displacement at that point is equal to the vector sum of the displacements due to the two waves. Right? So the net brightness that I would get at point A would be the vector sum of the brightness due to wave reaching from B and vector sum of brightness due to wave reaching from C. Right? Next, what do we understand by interference? The name of the chapter. Now, when we talk about interference, it is a phenomena of enhancement or cancellation of displacement. See, I have point A, I have rays starting from B and C reaching point A. Right? Now, if both the waves are in phase, if wave reaching from B and wave reaching from C are in phase, then the vector sum will be the addition. Hence, the brightness, let us assume that if the brightness is 2 here and 2 here, magnitude wise, then the total brightness at point A would be 4, right? Hence, what would happen? There would be an enhancement in the displacement that is going to be produced at point A. Similarly, if wave B is this way and wave C is 360 degrees out of phase, 180 degree out of phase, this is B and this is C, both of 2 and 2. Then the net displacement at point A will be 0. Point A, in spite of two rays reaching point A will still be black. So there would be, in that case, a cancellation of displacement. This phenomena of enhancement or cancellation of displacement at a point is called, due to superposition of waves, is called as interference of wave. So what do we understand by interference? Either the brightness will increase or the brightness would decrease, and this phenomenon of increasing or decreasing brightness is called as interference of wave. Right, let's write this down. How do I define interference? The phenomena of enhancement the phenomena of enhancement or cancellation, the phenomena of enhancement or cancellation of the displacement produced due to superposition of waves, the phenomena of enhancement or cancellation of displacement produced due to superposition of waves arriving at a point in the medium is called interference. Fine, do we understand what is interference? Now, when we talk about interference, there are two different types of interference. One, you can have constructive interference. Constructive interference. So what is constructive interference? If the two waves reach at the point simultaneously such that the resultant displacement at the point is the sum of the two waves, then it is constructive interference. What I showed you here. If both are in phase, if the two waves reach at the point in phase, if the displacement due to the first wave is 2 and the displacement due to the second wave is also 2, and the total displacement at point A is 4, then that is called as constructive interference, right? If the brightness at that given point is enhanced, then that is called as constructive interference. Fine, will you get this thing here? So can you write that? If the waves arriving at a point are in phase, their displacements are always added. Their displacements are always added to each other, and as a result, the resultant displacement at the point is maximum, and this is called as constructive interference. Right? When you have maximum displacement produced at a point due to two waves arriving at a point, then that is called as constructive interference. Next, you have destructive interference. What do we understand by destructive interference? Destructive interference, suppose if the two waves arriving at the point are out of phase. One is 2 and the other is minus 2. As a result, what will be the net displacement at point A? 0. There will be no brightness produced at point A. Such kind of interference would be called as destructive interference. Right? In the case of destructive interference, the displacements which are going to be produced due to the two waves will oppose each other, because the two waves are out of phase, Hence, the resultant displacement at the given point will be minimum, and that is called as destructive interference. Fine, do we get this in here? This what I showed you was an example of destructive interference, where this is +2, the displacement produced due to wave B, and this is -2, that is the displacement produced due to wave C. +2 -2 cancel, and hence the resultant displacement produced at point A would be 0. That would be called as an example of destructive interference. Fine. So let's write this down. What is destructive interference? If the waves arriving at a point of the medium are out of phase, their displacements always oppose each other. Their displacements always oppose each other. Right? And the resultant displacement at the point in the medium and the resultant displacement at a point in the medium is minimum. This is called as destructive interference. So destructive interference. Right? So thus, do you understand what is interference? Interference is the resultant displacement that is produced at a point due to two waves arriving at a point. What is interference? It is the resultant displacement produced at a point due to two waves arriving at a point. Either the resultant displacement could be maximum or it could be minimum. When it is maximum, it is called as constructive interference. When it is minimum, it is called as destructive interference. Fine, do we get this thing here? Now, what do we understand by steady state interference? Now I have two waves arriving at a point, right? I have two waves arriving at a point from A and from B. I have two waves arriving at a point. Now the two waves could produce, let's assume, first let's consider that their amplitudes are equal. If their amplitudes are equal, let us assume that the amplitude of wave A is 2 and the amplitude of wave B is also 2. Right? What are the different amplitudes that can be produced at C? Either I can have the vector sum of 2, 4, or if they are out of phase, slightly out of phase, 3, 2, 1, 0. I could have so many different amplitudes produced. Right? Depending upon the amplitude of displacement that is produced at point C, you would have different shades produced. I can have from bright to slightly less bright, grey, darker grey and black. I don't want that. What I want is, I want exactly, either I should get a bright point or I should get an extremely dark point. I should get an extremely bright point or I should get an extreme dark point. I should get maximum displacement or I should get minimum displacement. I don't want an intermediate displacement. The displacement that should be produced at point C should either be maximum or should be minimum. Such an interference would be called as a steady state interference. Fine, do we get this thing here? What is steady state interference? Where you have either maximum displacement produced at point C or you have minimum displacement produced at point C. Fine, do we get this thing here? The intermediate displacements are not produced. I want an interference pattern where I have extremely bright point, that is maximum displacement or minimum displacement, and that would be called as a steady state interference. Fine, do we get this thing here? Okay. Now if I want, do we understand what is steady state interference? I want either maximum displacement or minimum displacement. Question, how do I produce such an interference pattern? There are certain conditions that have to be fulfilled to produce a steady state interference pattern. Let's see what are the conditions required. Conditions for steady state interference. Let's see what are the conditions required for steady state interference. First, the two sources of light should be coherent. Of light must be coherent. The two sources of light must be coherent. Now what do you mean by coherent? Coherent means they should be same in amplitude and phase. Now if I want two sources of light whose amplitude and phase is same, how do I get that? That can be obtained if the two sources of light have been obtained from the same primary source. If I obtain two sources of light from the same primary source, only then will they be same in amplitude, phase and wavelength. In order to produce steady state interference, the two sources of light should have same amplitude, same phase and same wavelength. Guys, let's try an experiment out. Suppose if I have a source of light, I keep a cardboard in front of it with a small hole in it. So light would move out in the form of a wave from here. Now I keep another cardboard here with two holes in it. This is pinhole 1, this is pinhole 2, pinhole 3. Such that pinhole 2 and pinhole 3, P2 and P3 are equidistant from P1. Such that P2 and P3 are at equidistance from P1. In that case, I would get two sources of light from P2 and P3. What would those two sources of light be? They would have the same amplitude because they've been derived from the same source. They would have the same phase and they would have same wavelength. In that case, I can say that the two sources of light are coherent. Fine, do you get this thing here? So when I say that two sources of light must be coherent, means they should have, the phase difference between them should be 0. The sources of light are coherent when the phase difference between them is 0. Right? So, how do I get coherent sources of light? To obtain coherent sources of light, instead of using two different sources of light, two images of the same source are used. To get coherent sources of light, instead of using two sources of light, two images of same source of light are used. Fine. Since they are images from the same source of light, they will always have a phase difference of 0, right? Since the two images are derived from the same source, their phase difference will always be 0. Right? And that's how the two sources will become coherent. Right? And that's how I'll get a steady state interference. Right? Next, The second condition required for steady state interference. The two sources of light must be monochromatic. Why can't I use a white source of light? When I talk about white source of light, a white source of light is made up of 7 colors which have different wavelength. And since they have different wavelength, they would have different phases, and I would not get a steady state interference. Hence, it is very important for me to use two sources of light which are monochromatic in nature. They are made up of single color so that both of them have the same wavelength. Right? Do we get this thing here? A source of light, if they have different wavelengths, then they would meet at different points. As a result, I would not get steady state interference. Remember, steady state interference means I should have either maximum displacement or minimum displacement. So a source of light emitting light waves of only one wavelength, light waves of only one wavelength are called as monochromatic sources. Right? Now, it is essential that the two sources emit light of the same wavelength. Only then will I have a well-defined, sharp interference pattern. Right? Next, the third condition required is that the two sources should be equally bright. If the two sources are not equally bright, let us consider an example of destructive interference. Right? When I am doing destructive interference, in that case, I should have maximum darkness. If the two sources are not equally bright, then instead of getting maximum darkness, I would get a gray point there. Instead of getting a black, I would get a gray shade, and that would not be steady state interference. For steady state interference, I should have either bright or I should have a dark point. If they are not equally bright, then I will neither get maximum brightness nor will I get maximum darkness. And if I am not getting maximum brightness and darkness, then that is not steady state interference. Hence, it is very important for me to have two sources of light which should be equally bright. Fine, do we get this thing here? I can say that the intensity of light is directly proportional to the square root of amplitude. The intensity of light is directly proportional to square root of amplitude. Right? Square root of amplitude. So equally bright sources have same amplitudes. Right? Equally bright sources have same amplitude. If the amplitude of the wave are not same, are not equal, then the points which will arrive, the waves that will arrive at the point will be out of phase, and the point will therefore not be completely dark. So if I want a completely dark point, I should have, and if I want a steady state interference, then two sources of light should be equally bright. Right? If the amplitudes of the waves arriving at a point are not equal, the points at which the waves arrive out of phase will not be completely dark. points at which the waves arrive out of phase will not be completely dark. Right? That's my third condition. Fourth condition, the two sources must be narrow. The two sources of light must be narrow, right? Now, this condition is necessary to obtain the two waves in order to get a very sharp and a clear interference. Otherwise, what would happen is you would have the penumbra cone that would be dark, and there would be a lighter shade that would be formed around the dark point. Suppose if I have a bright point here, there would be a slightly grey kind of a shade that would be formed next to the bright point. This would be my extreme bright point, and this would be my penumbra cone, as a result of which I will not get a sharp, clear interference. So in order to get a sharp, clear interference, the two sources of light should be extremely narrow so that I get only the bright point. I don't get a slightly darker shade next to it. I don't see the penumbra cone. Okay, I see only the umbra cone. Right? So I can say that this condition is necessary. Condition is necessary to obtain sharp and clear interference pattern. Sharp and clear interference pattern. Fine. Next, last, the two sources of light should be close to each other. The two sources of light should be close to each other. The two sources of light should be close to each other. If this condition is necessary to produce sufficient separation between the two regions. If they are not close to each other, if they are far apart from each other, then the bright and the dark bands will be very closely spaced to each other. If you want an interference pattern where the bright and the dark bands are sufficiently far from each other, then the sources should be close to each other. If the sources are far away from each other, then the white and the bright and the dark bands will almost merge each other, and you will not be able to see a clear interference pattern. Fine, do we get this thing clear? I can say this condition is necessary to produce sufficient separation between the regions of brightness and darkness. The regions of brightness and darkness. Right? If they are not close to each other, if the sources are not close to each other, then the bright and the dark bands will be closely spaced. Then the bright and the dark band will be closely spaced. So those are the conditions required for a steady state interference, right? All these conditions were satisfied by an experiment called as Young's experiment. His experiment is also called as the pinhole experiment. Exactly what I showed you for coherent sources. He took a source of light, he placed a partition close to the source of light with a small pinhole in it, right? So this is my S1. From here, waves of light are going to be given out, right? Then he placed another partition and placed two pinholes in that, such that the two pinholes are equally spaced from the first one. The two pinholes are equally placed from S1. So he got S2 and S3, right? You have waves of light given out from here, right? When they reach S2 and S3, they will act as secondary source of light, right? And I would have an interference pattern that would be produced on the screen. I would have an interference pattern. You would have waves of light given out. Right? Similarly, from here also you would have waves of light that would be given out. And I would have an interference pattern that would be produced on the screen. Right? Which would consist of maximum intensity and then the two sources combined, and here you would get say minimum intensity and then same way minimum maximum, that's the kind of intensity that you would get where the two waves are intersecting each other, right? So this is the interference pattern that you would get, right? Do we get this thing here? You would get a steady state interference pattern consisting of alternate bright and dark bands. Fine, do we get this thing here? So, this is also called as the double slit experiment. This experiment was done by the scientist Sir Thomas Young in the year 1801. Right? Now, let's try to understand the experiment. I can say in the experiment, first, S is the pinhole illuminated by a source of light. This is my S, is a pinhole illuminated by a source of light. S is a pinhole that is illuminated by a source of light. Light emerging from S is allowed to fall on two more pinholes, S1 and S2. We'll call these as S1 and S2. Light from S is allowed to fall on two other pinholes, S1 and S2. Fine, do we get this thing here? Now, so these two pinholes S1 and S2 serve as coherent sources which ultimately give rise to secondary spherical wavelengths of equal amplitude. I can say these two sources S1 and S2 serve as coherent sources of light and ultimately give rise to secondary spherical wavelength. Wavefront. right, of equal amplitude, velocity and wavelength. Of equal amplitude, velocity and wavelength.
So can you explain the third point?
In this case, you would have two coherent sources produced. Since both these sources are derived from the same source, therefore the two sources of light that will come out from S1 and S2 are going to be in phase. In phase, that means they will have the same amplitude, they will have the same velocity, they will have the same wavelength. Right? Do we get this in clear? So thus, light emerging from S1 and S2 will give rise to steady state interference pattern on the screen. Since the two sources are going to be coherent, see, this particular experiment satisfies all the conditions. The source of light that I will use is monochromatic. The two sources of light will be close to each other. The two sources of light will be narrow, right? They will be equally bright because they have been derived from the same source, and hence they will give rise to steady state interference. If you check your conditions for steady state interference, these satisfy all the conditions for your steady state interference. I can say therefore the light emerging from S1 and S2 gives rise to a steady state interference. Gives rise to steady interference pattern. Fine, do we get this in here? Now, why do I need Young's double slit experiment? Young's double slit experiment is useful. Use of Young's double slit experiment. First, it is used to produce steady state interference on the screen. It is used to produce steady state interference on the screen. Second, the distance between the slit and the screen can be easily measured. Now see, I'll show you this experiment again. The first slit, the second slit, and this particular distance is called as D, that is my distance between the slit and the screen, right? Here I'm going to get maximum brightness, minimum brightness, maximum brightness, minimum brightness, maximum brightness. I'm going to get a steady interference pattern, right? Now, the distance between the two slits, that is S1 and S2, can easily be measured, which is represented as D, right? And the distance between two consecutive bright or two consecutive dark bands can be measured. This distance from here to here, this distance is called as X, right? So three things you can easily measure using Young's double slit experiment: the distance between the slit and the screen, the distance between the two slits, and the fringe width. This is called as the fringe width, the distance between two consecutive bright or two consecutive dark bands. So I can say that second point, the perpendicular distance between the slit and the screen D is measured, right? Next, the distance between two consecutive bright or dark bands, X is measured. And last, the distance between the two slits S1 and S2, the distance between the two slits S1 and S2, which is small d, is measured. Now, using this, Young found out that the wavelength of monochromatic light, the wavelength lambda of monochromatic light lambda can be given by the formula xd by d. The wavelength of a monochromatic light is nothing but fringe width into the distance between the slit divided by the distance from the screen. Fine. So do you understand how do we use Young's double slit experiment? Young's double slit experiment gave us the formula for the wavelength of light. Fine, do we get this thing here? Next. What is the importance of this? This was the first experiment that demonstrated the phenomena of interference of light. So, fourth, fifth was the first experiment to demonstrate the phenomena of interference. Right? Next, the experiment also proved conclusively that light is propagated in the form of waves. It proved conclusively that light travels in the form of waves. Next, and the wavelength of monochromatic light, as I told you, could be easily determined. Right? It also helped you. The wavelength of monochromatic light could be determined. So those were the advantages of Young's double slit experiment. Fine, do we get this thing clear? Next, let us see the conditions for bright and dark band. Conditions for bright and dark bands. Right? Now, if two beams of light are propagated through the medium at a point, they will simultaneously arrive at a point and they will interfere with each other. Now, if two such beams of light are in phase, then there will be constructive interference resulting at a bright point in the medium. Right? I can say that if two beams of light propagating through a medium arrive at a point of the medium simultaneously, then they superimpose and interfere with each other right? Now, if the two beams of light are in phase, then constructive interference will take place. If the two beams of light are in phase, then constructive interference will take place. Right? Constructive interference will take place, resulting in the intensity of light being maximum. Resulting in intensity of light being maximum. Now, how do I get this maximum intensity? Now, that means the condition required for a bright point is that the two waves must arrive at a point in phase. I can say therefore the condition for maximum intensity is that the condition for maximum intensity is that the two waves must arrive at a point. The two waves must arrive at a point in phase, right? Now, if they are in phase, that means the phase difference between them has to be zero. They will be in phase if the phase difference between them is zero. That is, the phase difference between them should be either 0 or 2 pi or 4 pi or so on. 2 pi because the complete wave gets over at 2 pi. Now, a phase difference of 2 pi corresponds to lambda, but phase difference of 2 pi corresponds to path difference of lambda. 2 pi means one full wave, and one full wave means wavelength is going to be lambda, right? That means therefore I should say that the condition for bright point is that the path difference should be multiples of lambda, path difference between the two waves arriving at a point, should be either 0, lambda, 2 lambda, 3 lambda and so on, right? Therefore, condition for bright point is that the path difference should be equal to 0, lambda, 2 lambda, 3 lambda and so on, which can be written as n lambda, where n can be a number from 0 to infinity, right? So that is my condition for bright point. So condition for bright point is that the path difference should be lambda. Next, let's try to get a condition for dark point. Now, if the two beams of light arrive out of phase, then there will be a destructive interference resulting in minimum intensity, right? If the two beams of light arrive out of phase, then there will be destructive interference. Destructive interference resulting in minimum intensity. Right, there will be destructive interference resulting in minimum intensity at the point. That means the condition for dark point is that the two waves should be out of phase. The condition for dark point should be that the two waves are out of phase. Right? Two waves are out of phase, that means the phase difference between them should be 180. That is, when one wave is going up, the other wave should be going down. That means the phase difference between them should be 180. That is, the phase difference between them should be pi, 3 pi, 5 pi, 7 pi, and so on. If the phase difference between them is this, then the two waves will be out of phase. Now for this phase difference, I can say what? Phase difference of pi corresponds to wavelength of lambda by 2. Right? If I say that the phase difference is pi, that means the wavelength should be lambda by 2. It corresponds to a wavelength, or that is your path difference should be lambda by 2. Only then the point will be dark. Therefore, I can say condition for dark point is that the path difference should be equal to lambda by 2, 3 lambda by 2, 5 lambda by 2, pi I am substituting as lambda by 2, which can be written as n plus 1 by 2 lambda, where I can say that n is equal to 0, 1, 2 and so on. So these are your conditions for bright and dark points. These are your conditions for constructive and destructive interference. Right? We stop this here for the day. Thank you very much.